this computer. Should hear something. Oh yeah. Okay. You guys, that's why you're here. I think it's recording. Let me see my mic volume. My mic volume, I can raise it. Let me share the screen. Share the screen, share the whole thing. So I want to share a bunch of stuff. Yeah, so I really want to talk about the second bullet point. But it's sort of an awkward way to start with the second bullet point. So the idea is basically that we have a bunch of HTTP microservices or endpoints, and it would be cool to be able to just create sort of new endpoints for free, so to speak, by basically manipulating them. Maybe the result of the first endpoint is being passed to the next endpoint, or maybe the endpoint requires several input, the kind of things, right? And you say, okay, I know these five, but I don't know these two. So now we have a new endpoint, which is the remaining two needed. Basically, you have a sort of like a language for manipulating endpoints. This is sort of my goal, but it's sort of not how this thing started, and it's sort of awkward place to start. So I will start with this. Basically, we'll talk about separation of UI and data. And we'll talk about logic solver, which will populate the data. So the story will be like this. We have, presentation, which is a bunch of UI components, right? Hierarchical presentation. We have a data, which is like data, right? And the data is presented. There's this two-way binding process, which basically takes the data and maps it to the UI. If user types something in the UI, that automatically gets pushed into the data. So this is two-way binding process. But the data itself, instead of us populating it with some sort of a program, we'll use kind of a homegrown logic solver that probably, Jason, you wrote. They may have been involved in it. It was way before my time. So this is, yeah. So what I'm trying to do, I'll actually show you an old, no longer properly working Haskell application and how we used to write it. We actually run it. And then we'll show you a new way that tries to accomplish this same thing, but is kind of exposed to people writing Python code, not needing to use Haskell. So this is the first goal. I will want to talk a little bit about type-based dependency injection, because this topic that I really want to talk about, the manipulating data, we don't have one way of doing it. We have two different ways of doing it. One of them is based on lambda calculus. Hindley-Milner type half of the lambda calculus. I'll explain what it means if I have time. The other one Jason doesn't know about, and it's based it's based purely on dependency injection. The idea is this: if you have these endpoints which have inputs and they have outputs, I have a concept of type-based dependency injection. So I can, I have a first input, I have a first endpoint, which I can dependency inject all the information into it. It gives me an output, which I put on the context of my dependency injection, and I can use it in my next endpoint, which can now use the data that is returned from the first one, and so on and so on and so on. And that leads to a different way, which I will try to show you if I have time, to basically manipulate endpoints, which is more imperative and maybe not as cool as lambda calculus, but it's sort of interesting in its way. So this is the plan.
And the second one is actually what people are using now, right?
Yes. Well, not everywhere. Like, the templates, the Word templates and stuff are still basically using expressions because it would be extremely hard to change the templating language to something completely different, right? Yeah, so we're using it. You can, the application I'm going to show you, because I just wrote a quick application as a demo, doesn't use any Python. It uses only the new way of writing the combination of inputs. Cool. So, well, we can have a look at this. There will be a little bit of criticism. So basically, most of this stuff is, okay, we maintain programming language, we maintain language solver. The rule of thumb is, any change is breaking. You're fixing a bug, you're most likely breaking stuff. This is probably the hardest part of it. Now, if I have time, maybe I can actually explain what we're trying to do to elevate this. We have very strong compilation warning delivery, where I can tell people, hey, I would really want you not to do this. I want you to do that. The static analysis allows me to maybe impact how people are organizing the code, which is good. At the same time, allows me to say, hey, this thing will not be available soon. Please do something about it. We also have a compilation flag similar to kind of pragmas in Haskell, where we say like, well, you know, instead of me fixing it, I'm going to keep it as is. I'm going to give you a different option where this is fixed, but you need to opt in for it. So all these things are maybe worth in talking about, but I don't think I'll have enough time in 1 hour to do that. So we'll see. We'll see how far we can go. So let's start with the demo. First off, yeah, so we're writing applications in several different types of applications. We're writing applications which are web applications. We're writing applications which work inside Microsoft Office, and that's one of them. This is Linux. I don't have Outlook installed, so I'm using online Office to show you something. And we also have like bot applications, which basically have no user interaction, but are working behind the scenes to make process emails. So this is the three big areas of where we're writing applications. So here I have, I need to sort of persist this so it doesn't disappear. I'll first show you example app. So example app is interesting because the example app is looking at the email, sort of looking at this content, and is getting this information out. It's getting this information out with this little weird highlight, which looks kind of pinkish, sometimes bluish. I don't understand why this is the color. This is rosy. One, maybe we just change something. It used to be yellow, but then it was blue, and now it's kind of rosy. But what this thing is actually, all this data has been populated by the logic solver, and I'll explain to you how this came about. So logic solver populated all of this by looking at the subject. So if I go to the other email, see different stuff got populated. And so what this application does, it actually allows me to take this email and put it into the document management system. So it's going to, if I click file, it's going to, so what I'm doing, I'm using kind of a development environment, which is very open. There's no like proprietary information here. We can clearly expose it to anybody. And we don't, in the document management system is kind of fake. It's mocked. So I'm going to click on file, and you get this sort of like, hey, success, the file, I uploaded something with this name, and this is the ID. Yeah, so this is the first one. So this is the new one. I'm going to show you in a moment how this is implemented. But I'm going to show you the old one, which doesn't work anymore. It doesn't work anymore because we changed this front-end piece. So inside Office or inside obviously web, there's actually a JavaScript engine which allows you to write what these are called add-ins. And we changed this front-end piece, and it doesn't understand all the instructions being sent, the UI instructions being sent. from the application. So you have these weird things that, which basically says HTML is not recognized yet. HTML is the kind of an instruction name or component name which is not recognized. So this is because this is old. Nobody uses it. But the whole thing works. See, it's still populated, this thing. And this is the interesting bit. When I define the preset, I kind of tap out. Takes a little bit of time. It actually got populated a bunch of other stuff. So what this logic solver does, it tries to use all the data that, do notice that this guy is not rosy, it's white. It's user entry. If I would change something here, it would immediately become white because it's not populated by this logic solver, right? But what okay, so what this thing does, you have the data, you have several elements in it that are populated but are known because user has entered them, and it's smart enough to figure out how to populate the rest based on what is. Yeah, so this is sort of like a little bit more, So I'm lying a little bit. It's not really so logic solver, what it means, right? Let me go back quickly because I kind of forgot. Maybe this is important. If you're not like, who programs with logic solvers, right? So to have a logic solver, we need to have types. Because what logic solvers do, you give them a sort of a proposition and gives you a proof, right? So alternatively, you give them a type and it gives you a program, right? So we need to have types. So if we have types, we will get this thing for free, sort of, right? Because now the data, we have types over data that we'll be using in this HTTP endpoints. And we also sort of need to have this to even go anywhere with it, because well, you give in a type, it writes a program in what? Well, in this language, right? It makes sort of sense. So this is sort of all comes together, sort of. It's not really logic solver because logic solvers are purely static, and if you think about it, user can populate different data elements, and this guy needs to be able to sort of figure out what to do with different combinations. So you would have to pattern match on what, like if you think of a data sort of like a record, which has n fields, you need to have 2 to the n pattern matches to be able to do all the possible entries. That's just static blowout, right? So it's sort of, so this is really doing it at the runtime, but still it's sort of pretty close, right? If you imagine in your mind that you have blown this out into all this pattern match, it's sort of like it could be done statically, right? Okay, so the next step I want to do, I want to show you the Haskell code for the old applications we just seen. And then I'll show you the new code. The old one is going to motivate what's going to happen with the design of the new code. And this is all JSON stuff. So far. Okay, so this is the old application. So the old application has this type called file data, yes. And that and these things that corresponds to either field or some nested record type or some algebraic data type that corresponds maybe group of fields. And you probably, if you know what HKD pattern is, you probably are sort of recognizing it. Should I explain what that is? Yeah. Well, so the idea is you can maybe give it something like a maybe. And now each field becomes either nothing or something, right? But you can give it something much more elaborate. You can give it something which marks the data that is like entered by user and marks the data that will be computed by the logic solver. And maybe have some other things, right? So you're flexible to put many different apps. What we have done in JSON have not seen, we have pretty interesting use of F. We're using it for golden test asserts. So we have an algebra of asserts. We can say like, I want this field to be equal to this or equal to this and not something, blah, blah. Basically, you can compose these by putting an interesting F, which looks a little bit like a kind of a Boolean algebra, right? But I'm not going to talk about, I'm not going to show it. So yeah, so it's not,
So,
yeah.
in a way, this is kind of like a decoder then too, right? The data's coming in, right? It's decoding it with different types.
Yeah, so this has JSON instances, so it's being decoded automatically. I didn't write any code for this.
Okay, okay.
You just need to sort of have correct naming convention because this is automatic derivation, right?
Okay.
And you see it's being decoded into this maybe functor. It's going to the partial functor, which is this thing that has these smarter constructors of like remembering what user entered, what this guy entered, is the computational functor that we use for this guy, right?
And so the maybe in this case, like when you're reading the JSON, if there's missing fields, they just end up like missing field is no problem, just
Yeah, there is a constructor for it in the one that you sort of like working as well, right? So this is the HKD data, right? Which we sort of have, we used to have. There's a bunch of stock derivation, which is like basic boilerplate. And then the important bit is, I keep scrolling until I find it. I had it a moment ago. Yeah. It basically tells the logic solver what pieces of Haskell code are allowed to be used in finding out the remaining fields. So these are all the pieces that the logic solver can use. Every of these pieces is an arrow. Arrows are so okay.
Oh,
An arrow, yeah.
The arrow.
yeah,
Yeah.
I'm,
So
yeah.
So
I'm sort of going along because you were telling me about arrows last time.
Yeah.
And it's slowly clicking, but
so
it also helps that I've written Elm, so I can kind
Oh,
of
right,
sort of
yeah.
grok this a little bit, and that helps a lot.
right. So here it is the best way to think about maybe arrows. Arrows, these are actually not arrows per se. These are semantic arrows. So these are actually arrows. So arrow is basically a piece of Haskell code, which I can show you. There's a bunch of all these things are arrows. So I can show you like this. So the arrows have this do syntax. So monads are things, or like applicatives or functors are things which are parameterized by sort of like a value. So you have you have some sort of value and you put it in some sort of monadic context and it's a monadic value.
Yep.
Arrows are things which inputs and outputs, but they're more generic than functions.
Okay, but would they work in the same sense as like what I was talking last time in Ruby, right, where it's a pipe? So it's in this case,
Yeah, for sure. So
if it's a success all the way through, right?
so
Or
this-
failure,
this-
it stops and then bounces out.
This is the do syntax which actually works with sort of piping. I want to run.
Okay,
I want to take this input and use this arrow to create this output. And then I want to take this output and use this, right?
yep.
So this is semantic arrow means that it's kind of effect system that probably Jason also wrote. It's definitely somebody before me.
This is, I mean, this is actually, this is pretty old. right?
Yeah, this is pretty old.
I mean, this is not what we were doing even 2 years ago, it's probably like.
Yeah, well, this is probably how we used to do Haskell stuff, what I'm going to show.
When you say pretty old, I mean, you started the Haskell, right?
Yeah.
Okay.
Yeah.
Was it, I think
It was like 8 years. That's right, there's no Haskell created.
this is kind of modern as far as Haskell goes, Haskell applications go. I think.
I'm just saying, that there's many sins of mine that we'll go through here, this is one of the original.
So,
Yeah, but you're definitely cutting edge stuff at the time at which it was done. I mean, even now.
so these are syntax trees, right? So basically, so all of this stuff that goes into it are really like more like just constructors. And you need to sort of pattern match all these constructors in some general sense. And so, okay, you say like, if this pattern matches, then use this implementation, otherwise use this implementation. So you're separating the code which does this arrow from actually implementation of what this thing does. So this arrow says like, hey, I want to use a logger effect. I want to be able to use exceptions. I want to use reader X, whatever that means probably I can get this information, right? And client X is basically a servant client effect for this. So I'll be talking to the file API. But this is all just kind of syntax. This is constructors at this moment. This is just syntax tree, and there is this code which basically compiles them. So semantic arrows actually are super cool. Arrows as an effect system is actually a super cool idea, but I don't really see it being used much. So arrow, you guys like those of you know what arrows are. Arrows have like several different flavors. And there is kind of basic arrow, there's arrow choice, which allows you to kind of deal with co-products in the arrow sense.
Like forking, like one or the two,
Yeah.
one or
So-
two things are coming out.
So
Okay.
if you have 2 arrows, you can say, hey, I can go from co-product of like either to a co-product of either on the arrows, right? And there's also arrow apply, which pretty much is like a monad. So this, from the point of view of like computational power, semantic arrow has arrow apply, so it's pretty much monadic. But there is, I think, like Twig or is one of them well typed. I don't remember which one. The one which Richard Eisenberg went to. Where is this one? Where he went? Is Twig or this is well typed? Or
I think it's well typed.
well, maybe well typed. So they have this very interesting one. Because so if you say I want to have an effect system which is an arrow, but is not arrow choice, then you cannot use conditional statements on the result of the previous arrow when you create a new arrow. Basically, all your conditional logic needs to be static outside of the results from the arrow. That creates
which arrow to use, but yeah.
You can do like if else, you cannot do pattern match, you cannot do any of this. So this is super powerful because this language has very static execution plans if you get there, right? So you can do some fancy stuff, but we kind of don't do that, but it's still pretty cool because we kind of have unique, right? Yeah. So this is how we used to write code. So let's have a look at how we are writing it today. So I'm going to show you how the new stuff was implemented. And I'm going to show, there are 2 different ones. One is sort of like for you to get an idea, and the other one is actually what I deployed. This 2.4, I don't know what will happen to 2 and to 3, but that disappeared. But yeah, so this one I deployed, and this one is actually what I'm going to explain. So now we're writing this application. So the application has this schema file, so this is based on GraphQL. GraphQL is kind of a mainstream kind of configuration language for for the JSON endpoints, right? It's kind of weird. It uses, for example, uses the thing type to represent an object record-like thing, like indicating like and nothing else is type. Maybe I have no idea what the type represents. Why they use type here? So the way this works is this HK this HKD or HKD I mean, HKD or HKD
Higher kind of data.
data D. Or is it that one? Yeah. Yeah, this sounded looked to me wrong. So yeah. So these are implicitly have an F, little F in front of it.
So that thing we were talking about for the maybe or the partial.
Yeah.
Yeah.
It's like,
So it's hard to express it in a language like the mainstream language. Unless you put a bank, if you would do this, then this in GraphQL means this is not nullable. And we say, well, that's not an HKD, that's really the file.
Yeah, so that's like GraphQL does that. That was inherited from
Yeah,
GraphQL.
GraphQL. So GraphQL, we're not really fully extending GraphQL. GraphQL has like interfaces, inheritance, and all the stuff that we don't want to have. But we kind of we're expanding in different ways. So do notice that like file name is email subject, because that's how I want to get it from, right? There's this IAM client matter number, and there is storage location. They're all probably just strings, but they have different unique types. So we have this concept of like, this is an example here, of like, say, I want to have strings, but I want to make them unique type, right? So we're doing this a lot. So this is the thing that I will be populating. So this is nested. The storage location is actually, again, an object-like type, which has this is like a project number, pretty much, for us. This document management system has this concept of workspaces, where you upload documents. So this has a workspace name and workspace ID. So this is like where you want to put it. So yeah, so this all of it will be mapped to different fields. I'll show you in a moment how this is done. But before we continue, we have these things that the logic solver will now start considering to populate the data. So I basically have assumed Python code under the URL blah, which takes the email subject and parses out the client matter number out of it, which is the project number, which is pretty much identification of the location in the thing, right? And then another one, which takes the this project number and includes a proper document management system location where this thing should be put. So this guy is being yeah, exactly, right. Yeah, so this guy actually it's a type defined in one of the important schemas, which I'm not going to show you, but I'm going to tell you what it has. It's also a type, and it has all these two fields. So the logic solver now is smart enough to say, hey, I have this type, I can drill into it and actually populate all these fields. So by looking at basically bunch of these what we call atoms, which are basically representations of an HTTP endpoint, which has an input and an output, and we have these sort of building blocks, right? Think of them as axioms, maybe, right? And you give them to this magic box, and the magic box says, okay, I can do these things, and I'll start populating.
So it's basically automatically creating like compositions based on those types.
Model
right?
compositions is like
Yeah.
you can maybe
But like in the simple case, it'll automatically put together the parse and
Yeah,
look up storage and be like, oh, I
absolutely.
can get workspace reference out of email center.
Yes.
It's basically, it's doing backtracking in the space of,
Mhm.
well, I don't know if there's change on that,
No,
but
no.
sort of the
Well, it's pretty-
lambda calculus free, right? Fine line in the tree that gets you from A to B.
So this guy is smart enough to maybe like if this has several input parameters, then you'll be able to kind of get them from different places. It does a construction of
So it
the
can also basically say like, oh, you've given me enough information and inputs to build a storage location, which might then be an input to something else. So it can like aggregate them that way and then use that to
Yeah.
figure what's available to it.
yeah. So this logic model is Jason probably very much more about it than I can. I actually think about it in terms of directed graphs. So you have like you can think of this that I have this core information that I have that I can provide because I know about email, I know maybe what user has entered. That represents maybe a bunch of nodes on the graph. And each of, like, if I have something like this on the graph, I automatically have all the fields linked to it on the graph, directed, right?
Because that can just be expanding from like multiple arrows, right? Like,
Right.
So it's the same.
So if I have this atom which has several input parameters, then I can slowly start composing like, okay, I can create a type which has all the input parameters by adding them one by one and creating these arrows, creating the edges on the graph. So now the question becomes like, hey, how do you get from point A to B? Is how to find the shortest path maybe, which is like, but the graph is huge.
And it's not really a path, because you may have multiple nodes coming from multiple.
But you can actually go and sort of
But some
you
connectors
can create much bigger graphs when this actually is a path. You can look at this, okay, it's not a graph because it's I don't know what rule yet. There's no rule yet.
Like hypergraph.
Hypergraph, yeah, hypergraph. Rule is there's no rule yet is. It's Stephen Wolfram, this physics model of like everything is sort of like a matrix, right?
Oh,
Just call you rule yet. So basically, like no, let's not go there. So yeah, so there's a file email. The file email is an interesting one because I basically say I want to dependency inject all these things. Raw email, the email that actually I'm looking at, my application type, and I'm going to do upload and transfer to the receipt. So this is a good time to actually.
Wait, sorry, forgive me.
Yeah.
The dependency injection that you're doing there.
Yeah.
The injection is happening.
So let me explain why I'm doing it. So, okay, so there's a file email which is going to happen when you click the button. So before I go there, let me show you the layout of the front of the user interface. So this is an XML. We actually have now what you get designer for it. Jason, it's really cool and it's growing.
Oh, you're saying you can actually.
Yeah.
You've got.
Yeah, you can actually
cool.
compose it visually and actually see all the options that you have. You don't need to remember, okay, I need to know this component. Yeah, so it has a button, and the button is mapped to an action. And the action is uses atom file email. Right? So since we're here, let's have a quicker look at this two-way binding, because it's really, I think, kind of second to none as far as simplicity goes. So the data is sort of implicit. You can name it differently if you wanted to, but the main application type is by default called data. So we say file name is the data file name. So file name, this one, which happens to be a string. So like, right? So, and then client matter number is this data CM, right? And then we're going down into the storage location. And we're presenting a storage location in this nest. Right? So this works both ways. If user enters it, that goes, it populates on the data. If the data has it, user sees it. Right? It's pretty cool. So when user clicks the button, the file email atom is being called. Right? So like what can you ask? What input parameters can you ask this atom to have? So actually, let's do this. U for K instead of K native, because we have also open fast, which we don't have anymore. No. Oh yeah, I need to go to this one. Clearly. Oh my God. What the hell is that? You know what?
This is why demos.
Let me do a cached version. Because that needs to talk to a microservice to get a type system. Something is right.
Oh, it did, just not all.
Yeah.
Something that won't be friends.
Yeah.
Awesome.
Yeah, something
Like we're
like-
getting every letter, and now we're getting more groups of words.
Why is King validate? King validate. This is all I need. That should prevent me from even talking. But this sort of means that I'm talking to somebody. This definitely requires work. Let me see. I am on VPN. I am on. Let me. Yeah, but it's fine. I'm just switching out VPN, so that should be okay. Let me try to go on this one if it's actually deployed. Maybe. Oh yeah, I know what's happening. Yeah. Okay, this is all my fault. So Juve. I'm using. Yeah. So now I should be able to even doing the first one. Juve config minus m. Let's try this one.
You're not in the directory, or
Oh yeah. Yeah. Sorry.
you just switch back again.
Yeah, because I want to. Yeah.
Oh, so do you have to do the platform switch again on this?
Okay. Open stream. Something I don't understand. So I am in the second application.
What did you run in the first tab, in the first terminal, the top one?
The first one is the road. I need to be in the application.
Yeah, but you're running command there.
Yeah, but this is just
You don't really.
this is sort of puts me in the Kubernetes correctly. So let me try to run it actually in this one, because this is the I have totally don't understand what's happening. Java KN validate functions. No, exactly. Yeah, so it actually shows you the warning. This twice means this is review warning. it shows you that, hey, I'm not liking stuff about what this is done, or maybe requires somebody to review, but everything is sort of kosher, right? Why can't I do? Let me try to do it one more time. Should be able to do exactly the same thing. And this one. Sure, matter. Yeah, so this guy's happy, right? No, okay. So let's look at the dependency injection. So I'm going to inject something called help. Is it type? It's like a whole type hole. So it tells me that I can dependency inject the following big types. Unit null, which is problem programming language. It's impossible to kind of correct things. So we have two different units. One is called null, one is called unit. because unit ends up being in JSON an empty list, and it confuses everybody. And a much better unit is something that has a JSON representation of null. So we switched it, but it's like, okay, units, you can GUID is our kind of accession ID to know which session, user session corresponds to. Caller app, I can dependency inject caller app because I know what app I'm talking to. App ID is the same thing. This is the application ID for this will be my example. I can inject my application type, Juvo user, which is the information about the user, with like email, first name, last name, blah, blah, and a bunch of other stuff. Outlook context, I'm running it in this is an Outlook application. Inbox name, sort of important. This is sort of like emails have this lots of the inbox. So like you use for Outlook, this is becomes sort of like the name of your account, sort of like your inbox name. Raw email, which is basically bytes of the email. Email context, which is somewhat different than Outlook context because of historical reasons, we have two different ones. And the email context is a little more generic. It's also applicable for processing batch emails that are outside, nothing to do with Outlook. Email is, again, historical. It's like email context, but a little bit not as good. Action name. What action name? Error message shouldn't be here. This is sort of a for dependency injection or it's an oversimplification, which there's a ticket to fix. Right? These are the big types. So I can actually say, but I can ask for like something much more specific. Let's look at email context. One of them, right? Let's do it again. So instead of injecting the whole big type with all the information, I can inject any of these things listed here for DI. So email context can supply an email subject, email query, whatever it means, email plain body, email HTML body somewhere here. Here. Email message ID, email reference ID. So, you have conversation threads. So you can use these to actually, control the conversation thread. Person is like some type which represents we have a bunch of stuff, but I can directly get things like, yeah. So this is a list. So basically, the underlying thing is actually a pretty powerful lens. It's a traversal with type checking on top of it. So we can, given a Juvo type and another Juvo type, I can construct a traversal from this type to that type. If you know what it means, you explain more or less. It's like a lens. but it can have more than one focus, with 0 or more focus points, 0, 1, or many focus. So I have this is runtime. This is the runtime thing behind it. Is this one big traversal? But I have types which allow me to verify that is this traversal a length from type to the smaller type, or to the option of the smaller type. If it's one of these two, then I am allowing dependency injections to it straight from the get-go.
And so the other ones like extract will show the cases that are not lenses.
So then you need to use explicit modification in this sort of manipulation language that I'm going to maybe explain if I have time to basically use the, you can get the whole list and then you can use lengthy stuff to play with them. So there's like an extract step which says like, hey, gave me the first one or gave me first and everything and tail and stuff like this. So basically, this sort of gives you the idea of what dependency injection looks like. So the idea is this now: if I have a bunch of atoms, if I have a bunch of these endpoints, I can use dependency injection. My next atom will be able to use. I add the receipt to my dependency injection context, so everything, the receipt itself and everything in it that I can uniquely lend to, I can ask for in my next step. So this gives you the one way of manipulation. And I actually implemented this stuff. The thing that is deployed doesn't use any Python, it uses lenses on, it uses this manipulation things. So this is the file email. It's called molecule. And it is sort of redundant because it sort of shows up twice. The reason why it shows up twice because molecules can be replaceable. So I can have basically a different version of, you have a small molecule which I can say, I want to have, for this deployment, I want to use this code, for this deployment, I want to use this code. So this gives me this ability. Molecule has steps, can have like a catch if you want to. Do notice that exceptions are not typed anywhere here, so they're untyped. But we have basically ability to catch and throw. So what this thing does is, so this is just for the demo. I'm using this hardcode step, which hardcodes a lot of information that I need to upload, to use the upload raw email atom into this the document management system.
And so, sorry, this is YAML that.
Yeah. So you actually see it here because it's like we can potentially support all of it.
And so like your match there is like, here's the type that we're matching on, gonna match.
Yeah.
I don't know what the value means exactly there, but if it's a null, we're gonna throw, otherwise you just hold on to the value. So
Yes.
like that's like unwrapping the value.
Yeah.
From the option.
Yeah. So there is this for my uptype. I'm extracting worksite ID out of it. So now I have worksite ID in scope. I probably don't even need it.
So the type of that is an option. So then you have to next do the match.
So then I this doesn't make sense if the workspace ID was not populated. The user must have not entered something else. So I'll be throwing a message to the user if they have not populated. Otherwise, now I basically pattern match. It's called in some languages called narrowing. I basically narrow out the option out, right? Because in here I guarantee that this is no longer an option. So now I have a worksite ID in scope, and the worksite ID is something I need to call this atom because it has a non-optional parameter. I'm not showing you the signature. I can show you if you want. But it also needs all these other ones for it to get called. So I'm just hard coding this in one step. This actually is super, super powerful. So if I would like, should not, let me get rid of the, no, this is, where am I? This is the second one. This is the second, let's just put here. Now this should no longer compile. No. So it's actually really statically checked. Like I can't hard code a wrong value. It won't let me, right? It needs to have the right shape. So yeah, so this is no. So this basically gives you sort of an indication, and then I basically massaging this guy to get a receipt because the output from this atom was somewhat different. And I'm converting upload failures that come from this into a flow too. So basically sort of gives you an idea how this thing works. JSON has the original one was kind of much more interesting, maybe, because it's different, right?
Yeah,
So,
yeah. So, I mean, so I only heard, like Gareth had mentioned that Robert had done some kind of cool things for making a DSL, essentially to get, I don't know if the context here is maybe relevant to understand what the use case of a lot of this stuff is. So part of what the technology was supposed to enable inside of Holland and Hart was not just sort of building applications for lawyers, but actually allowing people that are not necessarily like professional programmers, to use kind of a low code type approach so that, if I'm a paralegal or I'm somebody who's working with those people, I can put together some application for all the different use cases inside of a law firm. So a lot of this was trying to strip away a lot of what was necessary for somebody to just get an application up and running. And I think this was,
Tim Charter is visual basic.
exactly. And we've arrived at Visual Basic. And so I think there was sort of a move to, give people building blocks that they kind of put together, and initially, hey, let's try to put those things together in Python. And I think now it's essentially like, let's give a YAML file that, if I'm following what the molecule concept is I've got kind of a set of steps. So those steps are really almost like here's the Mad Libs, structured Mad Libs that you're giving to people, right? You need to put this thing in here. Where are you gonna get that? Is that hard coded for this application? Is that something you're gonna pull from somewhere else? And it kind of uses the typing and the lenses to be able to guide people.
well,
So like, oh, I can grab this from here. Oh,
So-
you put the wrong type of information there.
So, but Jason, also for your context, so what was happening is people were writing atoms in Python, and they were not atomic at all.
Yeah.
The atom was like
Do all the things.
yeah, it was basically organic chemistry at least,
Yeah, sure.
right? And this was somewhat hard to maintain. And what this thing does is more you have a declarative sort of overlay where you can combine really small Python pieces.
Yeah, no.
And now these Python pieces may be more reusable because they're small, they're very specialized,
Yeah.
and you have sort of a way to sort of manipulate them into something bigger, right? Now I didn't mention the stuff of low code because I started with this is the criticism, right? Now you have the environment which any change is breaking change. Now let's go and expose it to people who are outside of our group. Let's anybody write a code. We don't even know where the code sits. Whom are we breaking? Right? It becomes a little bit engineering a nightmare. So hopefully right now we are the only ones who are writing.
Okay, yeah.
So this has sort of failed as far as like anybody can write it, right? So where are we time
What
wise?
are the solutions? I guess what we were calling before, solutions engineers, they're sort of putting together applications, essentially using this
Yeah.
YAML. So
More and more, yes. This actually is getting quite popular. And this started by basically being able to write scripts to do sequential processing of incoming emails.
Yeah.
We used to have a very rigid way of doing this. And now I said, how about I just allow you to write sequence of atoms and now dependency inject them, right?
Yeah.
And that grew into this and then became this, right? So I want to a little bit talk about the other approach, right? So this is based on lambda calculus is super cool. So lambda calculus should be sort of now be clear what it is, more or less. So this is actually super important, I think. So lambda calculus is like the oldest programming language and probably most important one to know. This is my belief, right? In particular, the Hindley-Milner type system that we use with it. Hindley was a logician. Milner was a computer science. They both came up with it about 2 years apart. Other extensions, other types over lambda calculus is like Gerard Reynolds type system, also system F. Gerard is currently still lives, a French logician. The guy created actually linear logic. Rust is using a little bit. And Reynolds is a computer scientist, was a computer scientist in Calgary. They came up with this maybe 2 years apart independently. So you have something that people are discovering on their own independently. Now, nobody ever is going to independently discover C. Never. So I think this is sort of like Phil Wadler has this talk, which he said, like, the Independence Day movie where the aliens attack, and they introduce a virus which looks a little bit like C program.
Yeah.
He's like, no. If aliens come here, there will be lambda calculus, right? It has to be, right? There's no way somebody else is going to come up with something like that, right? So lambda calculus basically has these two concepts. This is super cool. So lambda, think of basically a bunch of the expression which has a bunch of variables X, Y, Z, and stuff like this, right? And it has two building concepts. One is if you have an expression like this, you can put a lambda and one of these variables in front of it, lambda X, and that becomes a function that accepts this X, sort of like one function, and returns this expression. And this is called abstraction and application. Application was like this. If you have a lambda expression and another lambda expression, you can apply it by taking the first lambda, figure out what the variable name is, and substitute all the occurrence of this variable with what you gave it. This is called application. What I think Jason came up with is how about we have lambda calculus which doesn't have abstraction? You cannot create new functions. You can only use the functions I gave you. And these functions will be the atoms plus set of built-in operators that allow you to mess with them, which include composition, map, because functors are monads. If you fix the input, the thing is not, this is sort of like, right? Now, and an applicative one, because it's monads is applicative. So there's this bunch of basically preceded things you can use. So say you want to do a function composition in this expressive language, you would say like this. You need to apply composition to a function. What's left is something that still needs another function, right? So to apply it again, this thing, you apply it again to the second function. So that is sort of like you write these lambda expressions, and by writing this, but what's beautiful about this is these lambda expressions are constrained to basically your atoms. You can't do like, you don't have full flexibility to create functions. You have to use, you're seeding this with small set of possible things you can use this syntax with, right? So that's super interesting, super powerful, and it's still being used, but it ended up being somewhat cumbersome and hard to do, especially since I think what we seeded it with was like applicative. People have a hard time.
I didn't know what. yeah.
Like,
Well,
you're talking low code. Let's have a paralegal. Hey, let's do the applicative, right? And an FMAP, right?
Yeah.
No. So this is right. The selection of the building blocks maybe was a little bit too advanced. That's part of it. Part of it that you get this huge syntax trees, which was somewhat hard to read, to write. Yeah. So I actually have a bunch of examples probably here for expressions. I can maybe show you some. Sure. Yeah, it's pure. So this is sort of is. Yeah, so this sort of is grammar for it. In JSON syntax, because you could just write this in JSON. So you end up doing stuff like control click. Oh yeah, this is so to make it sort of work, I actually wrote probably like 1,100 lines of documentation for this. So there is like a fully documented expression reference guide, but it's still not being as much. So, so you end up writing stuff like you can do like pure because it's sort of applicative, right? So let's look at so now here is, for example, decomposition. How you do composition, right? That's what I said, right? You need to apply it sort of twice. So the fxn is the apply. Because it has two functions to apply, right? So you are applying composing atom 1 and atom 2. So you have to take the composition operator, which has two inputs. So you apply the first one, second one is left, so you apply it again. So that's sort of that became quite cumbersome. So here is applicative, right? So it's a little bit maybe too honest, but and
and the logic solver would go and
yeah,
basically this is the currency of like
yes,
you'd be like,
correct.
hey, I have this input and output. Tell me how I get there, and it would.
Logic solver is going to write this. Yeah, logic solver actually writes this. So it's yeah. So this is it for me, I guess. Any questions? Any we can go into Haskell obviously a little bit. I can show you around how this is done a little bit more.
So you said there's like solution engineers who work here that are basically writing those the pieces.
And I'm too actually.
Okay. And like, what is their background? Where? Like they're not.
They typically
CS graduates.
So we actually have a Princeton CS undergrad right now. Yeah, so some of the different backgrounds. Brad is kind of a senior in this capacity, and his background is data science, and he's kind of transitioned more to writing applications. Not so sure about other people's background. Taylor, do you remember what?
Yeah,
I think
they're people that like coding kind of thing, right?
Yeah.
So they were.
We had Ben here, and Ben worked for software company, also writing Python. I think he first worked here, then he went to software company and came back to work for us, and then he works for another software company. So yeah, lots of Python programmers pretty much.
I mean, part of the thought process originally too was, you kind of needed people. So Ben Southcott was a good example. He was actually he was a paralegal, right? He's like, oh, I want to do more development stuff. Like, hey, this is great. You actually can talk to, the attorneys and sort of understand the process and I need workspace ID. Some of those stuff it's just technology, but some of it relatively domain specific, right? So part of the idea was like, okay, somebody to kind of do the interactions with the different, kind of stakeholders in the firm that were attorneys. So instead of having them be first developers, second, having to learn the, legal space, you have somebody who's kind of leaning more towards understanding the domain, but kind of give them the tools to be able to kind of quickly turn that into applications.
Yeah.
And reuse things that we've got, right?
Yeah, but just right. The whole concept is somewhat scary to me because I'm like, okay, what do we do later? Like, how do we maintain all this stuff that people write, right?
And is this like reducing the amount of Python or slowing down the production of new Python? Is that like,
The ability to sort of manipulate this.
yeah,
Yeah. So the idea is basically that you write Python in a more atomic, precise way
oh, yeah, so you're implementing the atoms are
in Python, and then some of them just any endpoint.
Yeah,
Can be converted,
it doesn't
right.
have to be Python.
Right.
So one thing, just kind of we maybe
And then this orchestrator is kind of, it can put in the things from different languages.
Yeah. So right, so basically, like if you look at the actual schema I deployed, the atoms are actually. So I still have atoms here somewhere. This is a molecule, yeah. But you're right. So like the parse CM is still an atom, but is implemented by evaluating a molecule. So one thing that we ended up doing is we no longer use URLs because URLs didn't work.
No.
What the URL you want to call is like you don't want to put it in here because each caller you want to use different URLs. Some of them are the gateway, some of them are not. So we have more like an endpoint definition. You still use URLs, but we have an endpoint that is late converted to a URL.
So, yeah.
So this basically is like, hey, there's a URL behind it. So yeah, so this is still our atoms, but I implemented them as molecule.
Molecule, right? It's a composition.
So in the future, this will be directly molecule. At this moment, the logic solver understands atoms only. Those are the limitation. I wanted to show that before we finish references. So there is Jason's talk, which you can look at YouTube, which is, I think, how to program like a 5-year-old. Yeah. From Ranteconf. I'll post the link to this report. Really public.
Yeah.
And the other one is pretty interesting. So this is Berlin functional programming group. Chris, what's his name? Yeah, Chris Panner had this super interesting talk about doing something very similar to what we have done. How to basically rethinking functions in terms of like you want to have these atoms, and you want to constrain your ability to build functions to only use this small group of maybe like HTTP endpoints or something like that. And his approach was more like more using like profactors, which is sort of like a little bit more modern arrows, yeah, right. Except they don't have the nice syntax.
Right.
You never do notation for them. But yeah, so these are two interesting things. I also maybe flash the lessons learned because in order to say we criticizing stuff. So here is the sort of criticism of stuff you guys can sort of read it and how we kind of fighting it. So this is not trivial to basically have there's obviously challenges with doing logic solver or doing programming language. But the fact, I think there's also huge power in basically writing programming language. You can deliver stuff that you will not be able to deliver by doing this. And this just the simplified UI, I think, is huge. I mean, the way the simplifies writing applications is tremendous. So yeah, there is like for programming language, I think we are winning on the benefit versus cost analysis. I think that I think I would argue that we are doing good. We are doing like for JSON information. We are actually working on a pub registry, something resembling package
Oh, cool.
for the Java, which will contain basically ability to deploy existing Docker images with full versioning and schemas and stuff.
Oh, cool.
So like stuff like this, it's sort of you need to do if you have a language, right? Because like this stuff comes from free. I mean, you have place to put gems, right? In Ruby, you have Maven in Java, you have package in Haskell, you have a bunch of stuff that we have to do on our own. So a lot of stuff is extra work.
Wait, so are you running like a local package server? or
No.
you're doing both?
This is specially made for Java. So Java applications can. So we have a need to basically say this application has, has a version blah blah blah.
Yeah,
Is deployed to staging.
yeah.
Let's propagate the deployment to production. And the bits that are deployed needs to be sort of packaged.
Yeah.
So there's a packaging mechanism for the Java application which contains compiled Python code into Docker images plus, everything that needs to
The
happen.
schemas and,
Yeah.
types.
So this is the Diego's working on. I think this is like super powerful stuff. And it's going to help us because, we kind of have different solution now. It's more GitHub based, but we're excited about like doing this. This is next step. But yeah, so this is sort of, I guess,
You go back to those URLs you were listening.
the ones that the ones that are not URLs like this one.
The
YouTube
talks,
videos.
Oh yeah.
Jason.
I'm going to post the references. I'm going to post the references I'm going to edit the announcement.
Okay.
I hope I can. I have to do it today, I think, because otherwise it's sort of won't let me.
Oh, well, let you.
Maybe not, because it's already past. It can happen, right?
You can still comment on the event.
Yeah.
I can definitely add the comment. This is a public repo. So if you go to Juris Futura and there's this repo, it's HS image.
Sorry, you're saying there's this.
Yeah. So this is public. Sorry, I use my glasses. I don't want this. They changed the job repositories. Projects. What's this? They changed it. Looks completely different.
Oh, yeah, I did notice,
What's going on? So
at least I just saw minor changes in GitHub UI today. I was like,
Git
wow, this looks
Hub.
slightly different, that looks slightly different, but.
Oh,
yeah, okay, that's I can recognize. HS. So this is public repo. I'll post a link. Okay, so that's yeah. Any questions? I mean, like, should we? And like, I mean, like, we can go and I can spend. We kind of late in as far as time goes, but if you have any questions about like maybe how it's done in Haskell and stuff like this, I can maybe talk to you offline or. A lot of the stuff is just fixed. Maybe I show you just this.
Fix the type or fix the function?
Fix the type. Possibly, yeah. Yeah, but this is sort of like, yeah, so this is our type. The type actually ends up being fixed. So this is the Haskell representation of the Java types.
And what's the better way to do this?
Oh, just,
Just fix-
I mean, so it's just another type that's like, so fix. You know, like uses Haskell recursion built in. It's probably, I mean, you're using, is it what libraries?
Yeah, we're using recursion schemes from
Yeah.
Math,
Um,
and they're fixed based.
yeah.
Yeah.
But it's just, you can, basically instead of fix, which is like a concrete data type that, you know, you just like have this nested structure.
Sure.
You can have mu, which is the same shape as fix, but it builds up a thunk basically.
Oh,
That is just discharged by giving it the algebra or whatever that you want to do. And in my experience, it actually, like there's some nice reasons to do that, but I was actually surprised when I was doing a bunch of recursion scheme stuff that it turns out to be much faster
Yeah.
Interesting.
than
Yeah.
actually having like reifying the
So-
structure.
Recursion schemes are very much fixed based, right?
Yeah.
So the way this is done, it's sort of, you know, JSON explicitly type this, and then uses fix to create the actual type,
Mhm.
right? You can start with the actual type and use base, which is the template Haskell, to
Right,
create this
sure.
guy.
Yeah.
It may be somewhat more descriptive, right? But they're equivalent approaches. If you use that, you know.
Yeah, and yeah, you can like write type directly and then use that template Haskell to extract the pattern functor and then rebuild it, then use mu to create the thunked version.
Yeah,
of
sure,
the
yes,
thing
right,
also.
right. Yeah.
So, Brooke, at least since you, this fix is basically like, so it basically creates a recursive data structure. So this is like a flat data structure. Like, you know, all the different constructors that are scalar and union, whatever, they're like one node. And it's all just a functor. There's that A, right? So that each are parameterized over some type. And so the fix on that line 76 there basically tells it to make it recursive, to basically make the A effectively be type F. So it's like type F of type F of type F, kind of infinite recursive. So now you have a self-referential data structure,
Okay.
but you've never written that. You kind of separated those two things. One of the things that's nice about that is you can then like write operations over this data structure that only operate at one level. So you don't have to think about the recursion. You just say, oh, and I see one of these, I do this. So we do this. And then you can tell like, okay, now apply that over a tree of these things.
Yeah.
And so, and then there's lots of other things. So then you have a compositionality where you can do like a single traversal over a tree that actually does like, you know, 30 different things that some may depend on each other or things like that.
So-
Rather than having to do multiple traversals to get all the different pieces you need or
So-
whatever.
Yeah,
stuff like
that's,
that.
yeah, that's really neat.
So in other words, like you can have a list of scalars. Because the fix allows you to sort of nest them, right?
Yeah, yeah,
This is stuff like this basically, right?
Yeah.
And fix also is a fixed point. So functors in Haskell and the functors, they move types to types.
Okay.
A fixed point is an element where when moved by something it stays the same, right?
okay,
So minus nominal typing trick, because you need to sort of unfix it. Functor on the fixed structure is the same fixed structure. It preserves it.
okay,
So that's why it's called fixed. It's fixed point. It's a fixed point type
okay,
or a for a functor. Is the type that the functor doesn't change.
okay.
So basically this functor is not changing this type. So
Okay.
when applied.
That's sort of.
We sort of because the nominal type, right?
Yeah.
So you have to unfix it. You
Yeah.
cannot have these two sides be the same because one has an extra constructor.
Yeah, no,
Right.
But there's an isomorphism there.
But it's
Like
yeah.
unwrap it and wrap it back up and nothing here.
Yeah. So this is like the concept of iso-recursion. Iso-recursive.
Okay.
It is isomorphic. It's isomorphic. It would be good actually to maybe do a presentation about this. Just not me. No. Anybody else?
The very first Haskell meetup that I went to,
Oh,
was the
stop
one you
this.
hosted on recursion.
Really?
Yeah.
What was that?